Here we are doing integrals. You guys know how to do integrals. In BC, you nearly mastered integrals. We'll continue to do integrals in this class, but I'll admit that none of the techniques and things we use are really beyond what you're used to. There'll be certain types, it'll become pretty cyclical, you'll get really used to it. Doing double, triple integrals and things like that will not seem so bad because you're capable of single integrals. Remember, just talking through the idea integral. This is my integrand. This is my differential. This is my integral symbol with my bounds from a to b. If f of x is my original function, the antiderivative is the big f of x that comes out. And I know that integrals and derivatives are inverses, and they will cancel each other out. So if I integrated f of x and got big F, took the derivative, I end up right back where I started. That's what the fundamental theorem of calculus helps us with. The fundamental theorem of calculus also gives us some other things like, I don't know, average value. No comment. Here we go. So we are going to do some integrals. I'm not going to slow down. We're just going to run through this thing, right? Anti-power rule here. This goes to the sixth, so I add 1 and divide. That's what it says. Add 1 and divide. That's going to be 1/2 x to the sixth. I believe in you to do fractions. Right? None of you watching this video should have a question about that one. Here we go. Again, a nice little trick here. Let's rewrite this x to the negative 1/3 power dx. And so then when I add 1 and multiply by the inverse, it would be negative 3/2 x to the 2/3 plus c, because these are unbounded integrals. So I don't have an initial condition. I don't have anything I can tie it to. We will get that thing we can tie it to. So here we go. I think I just froze for a moment, but hopefully it didn't carry over too bad. Let's take this antiderivative here. That would be negative cosine x. You should know that. Plus sine x. I probably caught you off with that one. Now I don't need my plus c because that subtraction with the fundamental theorem of calculus, if this had a plus c and this had a plus c, they would just cancel each other out. So in general, we ignore the plus c, even though I technically should be writing it here. My bounds from 0 to pi. Again, I'm only going to write this out for the very first example, and you will not see me write this for the rest of the day. Sine pi minus negative cosine of 0 plus sine of 0. And then just evaluate this thing. I get negative 1 minus negative 1 to get 0. How clean. How nice. On to the next one. Secant times tangent. Hopefully you know your trig. That's all I can tell you. 1 second problem. If you know your trig, it's a 1 second problem. On to the next one. Over here, ooh, the integral of 3 to the x. I'm not afraid to give you something that you're not well practiced in. You should get used to these things. You're in Calc 3. Alright, I do the antiderivative of the first one. I do the antiderivative of the second one. Now, that's going to pop out in ln, and normally that ln would multiply when I have a derivative, but I have an integral. So this would be 3 to the x over ln 3. Ooh, what a nice one. And evaluate this thing from 0 to 1. E to the 1 plus 3 to the 1 over ln 3 minus e to the 0, which is 1, plus 3 to the 0, which is 1, over ln 3. I could probably simplify a little bit there, maybe combine the over ln 3's, but it's probably not worth my time here. 1 over x, just a good reminder here that this makes ln x. What a classic example. Plus c, because it's an indefinite, unbounded integral. We have no initial condition. And now we start to get into the good stuff here. Find this function given an initial condition. It says my derivative is 4x cubed. At 1, my value is 2, so I'll do it. I need to take, again, just for the sake of saying and showing. Right? That's just the truth. The integral of the derivative is the original f of x function that it's asking me to find. You need to write dx's. I'll ding you points over and over again. dx, dy, dz, d theta, dr, d rho, d phi will become so important in this class, and the order of them you cannot ignore writing your differentials. Here we go. So I'm going to integrate that 4x cubed dx. I'll get x to the 4th plus c. I'll use that initial condition to help me. F of 1 is 1 to the 4th plus c is 2. That means c is 1. That means my final function is x to the 4th plus 1. Just like that. Okay, find the position given that acceleration is based on sine, my velocity has an initial condition, and my position has an initial condition. There we go. And I know that when I integrate acceleration, I'll get velocity. So I'll do just that. The integral of sine t is negative cosine t plus c. Until I find that initial condition, it is a plus c. When I plug in 0, though, I'll get negative cosine of 0 plus c is 1. That's negative 1 plus c is 1. That means c is 2. So now that I know that Vt is negative cos t plus 2, I'll integrate that to get my position. Plus c. And repeat again. I'm going to plug in 0. This should make 3. It's going to be a negative 1, so my c is... Oops. Oh, that quick? Just like that. So actually, my c ends up being 3. So I get my final position function here. Negative sine t plus 2t plus 3. Sorry about space on that one. The box got just a little bit cramped. I believe in you to make it fit a little bit better than I did. Here we go. And like it says, as functions get more complicated, as things become inseparable, especially by multiplication and division, we can use advanced techniques. When you use a computer, it will manually calculate the values, and it'll be a little bit inexact. It'll use analytical methods, almost like an infinite Riemann sum, but we can do better than that. I know we can do better than that, so let's do just that. I'm up here at u-substitution. We should be able to do u-substitution. You know, when I use u-substitution, I find the innermost thing. I call it the anti-chain rule. So I know that, hey, I would set u equal to x squared plus 1. But that only takes care of one part of my integral. It doesn't take care of this x, and it doesn't take care of the differential. So I'll need to be really mindful here and take my derivative. But I don't need to get rid of a 2x dx, I need to get rid of a 1x dx. So I'll divide out the 2. And now my u sub is set up. I'll replace the inner function with square root u, and I'll replace this outer stuff with this du over 2. And I'll take my integral on that thing. That's a u to the 1/2. Yep. So it's going to add and divide. We get 2/6 u to the 3/2 plus c. And what I'll do is I'll just substitute back in this u and reduce that fraction. 1/3 x squared plus 1 3/2 plus c. Even on to the next one. There is no innermost function. But what I can definitely tell you is that I'm never going to put u in the basement. I'm never going to put I'm never going to put du in the denominator. So I definitely want to target ln x as my u. At least that's my first try. And if I mess up, oh well, I'll try something different. Alright, and I see that just by setting it equal to ln and taking that derivative, I found all the pieces. But one thing I haven't done, and one thing your teachers probably have not done so far with you, is this bound is technically x equals e, and this bound is technically x equals 1. So I need to re-evaluate those. If x is equal to 1, then u is equal to 0. If x is equal to e, then u is equal to 1. And so I've rewritten my integral now. ln x becomes u. 1 over x dx becomes du. And so I just evaluate this thing. Just like that. You know, I could show a little bit more steps, but you know it's going to turn out to be that. And when I change these bounds, right, this is from u equals 0 to u equals 1. It's going to look silly and ridiculous when we write it now, but when we get to double and triple integrals, I need to know what the bounds are and what variable they're talking about, and if it matches my differential. We'll see that later. Last but not least, integration by parts. I have this lovely formula for integration by parts. Right? That's what by parts does. It's not rocket science. It's just by parts. It's a little formula. It's whenever I have products of different types. When I have products of the same types, I'm going to be using u-sub. I'm going to be using anti-chain rule. But when I have products of different types, that's when I go to by parts. And I always want to set u to be the simpler derivative and dv to be the manageable integral. So when I do this first one, I'm going to set u to be x, because that's a super simple derivative, 1 dx. But then my dv is going to be the other thing, e to the negative x. And then when I integrate it back, I would have this piece. And now I just throw everything in together into the formula, negative x e to the negative x minus this integral of the two things that I didn't start with. A little simplifying here will go a nice long way to help us do this antiderivative. Don't forget your plus c. And I'll go for a little simplify out here on this one. Right? That's what by parts does. It just allows me via this simple formula, as long as I'm multiplying different types, and I hope that one of these simplifies a little bit nicely, it'll all work out. And I'll do the same thing down here, but it's a little bit harder on this one to choose which one's u and which one's v. I definitely know what the derivative of ln is, so I'll do the derivative for ln. Whereas I can integrate this x squared pretty easily. I know you'd think that this one might be the more manageable or simpler derivative, but that's a terrible integral, and we know that integrals are harder than derivatives. And so again, I'll hop back to the formula and fill everything out. 1/3 ln x times x cubed minus that integral of the two pieces I didn't use when I started, 1/x times this. And it actually turns out kind of nice, because the 1/x will reduce the power on this guy, and then I'll just simplify this thing again, another antiderivative. And it looks like I can simplify a little bit here, but I don't know how much it helps me. But I just like to. It's just a good check on your powers. And that's part 1 of your integral review. Part 2 will get into some other techniques. I'll also teach you a new one called trig sub that helps whenever you see the distance formula inside an integral. That'll be coming to you next. Happy integrating.